Hello and welcome to lecture 8 in the quantum field theory course. So having spent the last couple of lectures kind of tantalizing you saying we're going to be considering interactions, in this lecture we're actually going to write down some interactions. We're finally going to start quantifying them. As you'll see, however, there's still more formalism that we have to introduce. So the previous formalism we introduced was this whole discussion about the propagators, and in particular the Feynman propagators. In this lecture, we're going to see that there's a formalism called the S matrix, and there's a whole different picture we're going to introduce to allow us to deal with interactions and to make calculations. So just to give you a little bit of a recap in terms of what we've done. So at the start of the course, we solved this free theory of the real scalar field. So this was a theory without any interactions, and we saw that our field phi satisfies the Klein-Gordon equation. So now we want to move on and think about theories that have interactions. However, there's one small thing holding us back, and that's the fact that there's no interacting theories are exactly solvable when we work in 4 space-time dimensions, which we do live in 4 space-time dimensions, so it's kind of the number that we care about. Instead of trying to write down exact solutions, the strategy that we're going to follow is to model or treat our interactions as perturbations on top of the free theory that we do know how to calculate. Okay, so let's think about what interactions could look like. So we're still dealing with real scalar fields. We're going to stick to that paradigm. But we can start by writing down what interactions can look like by writing down the Lagrangian. So the Lagrangian is what describes the theory. So our Lagrangian will start with the bit that we wrote down before. But now we can add interactions, so additional terms to this Lagrangian to model interactions. The general form that we can write the interactions are some parameter lambda, and I'm going to label it by n, and we can have fields to the nth power. And we're going to consider cases where n is greater than or equal to 3. The phi squared terms fall under the category of the mass terms, so it's terms which are higher than quadratic, so cubic, quartic, and so on. So all of these lambda parameters are known as coupling constants. There'll be 1 for each value of n. In general, we've got an infinite series of terms here that we could be dealing with. In practice, though, we can restrict the form of the interactions that appear in our theories by imposing certain symmetries. Find this in all of our theories of particle physics, that symmetries can restrict the form of the interactions. Just give you one example of that. So, for example, if we require that the Lagrangian, so what we mean by a symmetry is some operation that leaves the Lagrangian or this Lagrange density unchanged, or technically, as we saw if you remember when we looked at the energy momentum tensor, it can change up to some 4 divergence term, which we exploited with the energy momentum tensor. But here we don't need to worry about that subtlety, so we're just saying that L is going to be unchanged. So let's consider what happens if we impose on our symmetry a so-called Z2 discrete symmetry. So in other words, we want our symmetry to be unchanged when we make the substitution that phi goes to minus phi. So if we want the form of our Lagrangian to be unchanged, we would find that imposing this symmetry excludes basically odd terms with an odd power. So this excludes phi to the cubed. Well, it excludes 5 to the cube, 5 to the 5, so any odd dimensional term, because could phi goes to minus phi in a cubed term, we don't get phi cubed back, we get minus phi cubed back, so we get a different term back. So that's one way we can, that's one way that the form of the interaction terms sort of narrowed down from this in principle infinite series. We do it by having symmetries in our theory. And then there's a second way. So typically terms with n greater than or equal to 5, sum, make n greater than or equal to 5, these lead to what are known as non-renormalizable terms. Realizable. If we have, say, a phi to the 5th term, we would have a non-renormalizable theory. So what's the issue with non-renormalizable theories? Well, you have to be a little bit careful with them, because you will find with non-renormalizable theories that you'll have terms that are infinite at high energies, which is basically a sign that the description of the theory is not correct. It's not that we shouldn't think about non-renormalizable theories at all. It's just that we have to be careful in dealing with them. So, for example, we know Fermi theory, the theory that Fermi wrote down to describe beta decay. That's an example of a non-renormalizable theory. But we know at low energies that Fermi theory gives perfectly good, respectable, accurate predictions for beta decay processes and other charged current interactions. Right? So Fermi theory is good at low energies. However, we know it's not an accurate description at high energies, because it doesn't take into account the fact that it doesn't even know. Well, it doesn't take into account there's a W boson and possibly a Z boson and all of these other things that only become apparent at higher energies. Okay. So we're going to combine both of these things. So we're going to consider a theory that has this discrete symmetry, and we're only going to consider renormalizable theories. So we're going to exclude terms with n greater than 5 to consider a well-known theory. We're going to consider basically the theory that's left. So it's a renormalizable theory with this discrete symmetry, which is the so-called phi to the 4 theory. Phi to the 4 is the only term that's left. So our symmetry knocks out phi cubed, and our condition that it's renormalizable knocks out phi 5, 6, 7, and upwards. So let's write our theory. So we can break our Lagrange density into two pieces. Let me call one L0. This is the bit that we've already dealt with, that we know how to solve, plus a new piece that I'll call the interaction piece. So L int. Okay, so L0 is piece that leads to the Klein-Gordon equation that we've been looking at. And I'm going to write L int following forms. So I'm going to introduce this 4 factorial factor, or factor out this 4 factorial factor from the coupling constant. So this is for convenience in this theory, where you get symmetry factors equal to 4 factorial, which will cancel this. There's some things we can say. So this coupling constant in this instant is dimensionless. It's a number. And so we're going to be solving this theory using perturbation theory. So very naively, we expect perturbation theory to work when the perturbation is small. Or in other words, if this coupling constant is small. We expect our perturbation theory to work. The magnitude of lambda is much, much less than 1. Okay, so that's the theory we're going to be thinking about in the rest of the course, this phi to the 4 theory. So next we'll go on and think about how we can calculate things in this theory. Okay, so we've written down our phi to the 4 theory in our Lagrangian formalism, but we saw that actually for canonical quantization we actually work in this Hamiltonian framework. So we want to take our Lagrangian or find the fourth theory and figure out what the Hamiltonian density should be. So let's start with the general problem, where if we have our Lagrangian in this form, so we have L naught, which is the piece we had before, plus some interaction terms that only depend on phi, do not depend on derivatives of phi, only phi. Well, we know that pi in these classes of theories is going to be the same, because pi is this Lagrange density, derivative of the Lagrange density with respect to the time derivative of the field, but our interaction pieces does not depend on time derivatives. So this pi field remains the same as it did for a Klein-Gordon field, so namely pi dot I, the time derivative of pi. Sort of an assumption we're assuming by definition that the interaction piece does not depend on derivatives of the field. Okay, but then this means that when we consider our Hamiltonian density, which is pi phi dot minus L, since pi is the same, it's the same form that we would have, we'll find that this is pi squared minus the L naught piece plus the interaction piece, which is going to give us, so this bit pi squared minus L naught is what we had in our previous theory, so it's what we had in the Klein-Gordon theory. So this is simply, let's call it H naught, so the bit from the free theory, minus L int. In other words, we could define an interaction Hamiltonian density. Then we see that our interaction Hamiltonian density is going to depend on the fields. It's just going to be negative the Lagrange density of the fields. Okay, so for the concrete example that we're looking at of phi to the 4 theory, it's simple to calculate what the Hamiltonian interaction density is. Just swap the sign, easy peasy. Okay, so our Hamiltonian, then the derivative over the volume, the integral over the volume of this interaction piece, so it's just going to be lambda over 4 factorial phi to the 4. Okay, so it's straightforward to work out what the Hamiltonian density is and also the Hamiltonian from the interaction Lagrangian. Okay, so we've sort of defined the type of theory we're interested in considering, so this phi to the 4 theory. Now, one of the reasons we want to think about interacting theories is because they give a more accurate representation of what we find in nature. The one thing in particular that happens in interaction theories is that scattering processes can occur. Okay? And this is, as particle physicists, this is how we often determine the properties of a theory. We do it through scattering processes. So being able to map our interacting theory onto a scattering process is something that's very, very important. So the way that we do this is going to involve something called the S matrix. S, I guess, is there for scattering. Okay, so let's begin by thinking about the setup of a sort of general-looking scattering process. Okay, so it's useful when thinking about scattering processes to divide the process into 3 regions. Okay, so we're going to have 1, 2, 3. Okay, so region 1 is what we could call the in region. This is kind of where we prepare our particles. Imagine we have a particle 1. This is a particle which maybe we're accelerating or bringing up to some speed somehow. So this particle 1 is going to, given a kick, or it's going to have some momentum, and it's going to travel, well, classically, it would travel on some trajectory. Quantum mechanically, what we do is we prepare our state, let me call it some in state. So typically this would be some momentum eigenstate. So give it We give our in-state some momentum, and we know how to describe those. Okay, so we have this region where we've just prepared the particle, and it's just traveling. Well, classically it would travel in a straight line, but it's not interacting yet. Okay. But then we do want to think about interactions. So we're going to then imagine that we enter some region where the particles do interact. So we're going to have a second particle, and our first particle is going to interact with it in some way. Now this is where it can be incredibly complicated, and we don't precisely know how the particle is going to interact with the other one. It's going to be in some very, very short, well, let's assume it happens in some very, very short distance scale. So there'll be the exchange of some particles and something will happen. But our particles are going to interact in some very potentially complicated way. But then after the interaction has happened, our particle is going to continue on. Then at some point it's going to leave our interaction region and go into a region which we can call out region. Okay, so the out region is similar to the in region. Then we have some, classically it would be going in some straight trajectory. Quantum mechanically, we're going to describe it with some well-defined quantum state, which could be, as I said, something like a momentum eigenstate. Okay, so we can actually, or we will sort of divide these three regions up mathematically. So when we think about time, we're going to assume that at some negative infinity time, that's when we prepare our state. And state is prepared, give it a kick, starts to move off, goes into the interaction region, interacts in some way, then goes to the out state, and then on the out state, we're going to model this as positive infinity. Okay, so we're thinking that our process goes from minus infinity to infinity. Now, there's an important assumption that we're going to make, or that we sort of have already made in the diagram we have above. Let's clear about what that assumption is. So we're going to assume that outside of the interaction region, in other words, in the in and the out region, these in and out, or initial and final states, are going to be eigenstates of the free theory. Whereas these are eigenstates of our H naught, the Hamiltonian of the theory that we know how to solve. Okay, so in other words, the particles aren't interacting out here or out here at positive time infinity. They're only interacting in this finite small interaction region. So let's think about why this should be the case. Why is this a reasonable assumption or constraint to put on our theory? Because it's not following, I mean, this assumption doesn't follow from some mathematics. It tells us that we have to assume this. This is a choice that we're putting in. So why is this a reasonable thing to do? Well, let's think about what happens intuitively. What happens intuitively at the beginning and end? Well, what we have, beginning and end, we're assuming that the particles are very far from each other. And certainly this is true in lots and lots of particle physics experiments. So, you know, imagine a long baseline neutrino experiment. Neutrinos travel for thousands and thousands of kilometers before they interact. Or maybe think about, again, neutrinos that come from the sun, travel through the vacuum of space, and then eventually end up in one of our detectors on Earth. Or, you know, even at the LHC. It's only at certain points in the beam pipe where you actually make the particles cross. So they basically have come from some huge distance away along these beams, and then at some point you force them to cross. Okay, so if at the beginning and at the end the particles are very far from each other, we should expect the effect of the interaction should be small. Okay, and again, this is true for a lot of the theories that we know about in particle physics. Not all, or not all of the theories you know about in nature. So gravity, of course, electromagnetism. Think about gravity, a long-range force. You have two, particles at either side of the universe and nothing else. Eventually, they will interact. But even still, if they're very, very far apart, it's a 1/r² potential. So the interaction is very, very small. So in our particle physics, most of our theories are short-range theories, so this approximation is even better. That's one reason why this is maybe a sensible approximation to make. And there's another one that we can do, another argument we can make, which is that before and after scattering, we don't expect the number of particles to change. In other words, we can have some electrons, say, let's imagine we have an electron-positron collider, we have electrons coming in, okay, they can interact with the positron in the interaction region and change into other types of particles. But then once the interaction is finished and they're moving away from each other, we don't expect the electron to suddenly change into some other particles. We're assuming that very, very far outside of these interaction regions, the particle number does not change. And so we saw in the last lecture that for free theories, this number operator is an eigen, or rather it commutes with the Hamiltonian. Because it commutes with the Hamiltonian, the NDT is 0. Okay, so in other words, one way we can force constant number of, one way we can ensure that there is a constant number of particles that they don't change is if they're eigenstates of our free Hamiltonian. Okay, so we can draw this another way. So above we had a scale, a time axis here, going from -infinity to infinity. So in a sense, what we're going to assume is the following. So let me draw time axis again, plus infinity, minus infinity. And let's look at the effect on the interaction Hamiltonian. Okay, so what we're saying is that very far, well, actually, let's do it in the following way. So if we have h, so we can have, call it h naught. Let's do h naught plus h int. We're doing what the Hamiltonian for the system looks like as a function of time. So at infinity, we're assuming the theory is just described by the free Hamiltonian. Our in and out states are described just by h naught. And then at some point, they enter the interaction region where the interaction operates, switches on, and then we have to use the Hamiltonian of the full system to model what's going on. So in our interaction region, the full h naught plus this interacting Hamiltonian are operating outside. It's their free part only. So in other words, we're going to assume this Hamiltonian bit is effectively 0 times, which we're going to call plus and minus infinity. So this is at the start and the end of our scattering process. Okay, so what can we do next? Next, let's define some more formalism. Let's define some states. Let's call them in and out states. These are going to act as a basis set for the in and the out theories. So we actually know what the in and the out theories are. These are for the 5-4 theory. This would just be the Klein-Gordon theory. Important. In out states in the free theory. This is important because we know how to solve the free theory. So we can bring across all of the results that we have found derived for the free theory. Okay, so I said the section was about the S matrix. So let's actually define the S matrix. Let's see how it enters the game. So the S matrix is an operator. So this operator set is called the S matrix. And what S does, so it's an operator. This is an operator that relates our out and in states some way. In particular, what we have is that, let's define our out state and in states. So what happens is that we start with an in state, this scattering process happens, and this scattering process is going to, if you jumble up all of our in states in some way, so something happens to our states because of the scattering process, and it ends up as an out state. So we're going to put all of that jumbling from the interaction into this operator. I'm defining it here with a dagger, or we can write it S in is S times the out states. Okay, and since this operator is going to be a unitary operator, so S dagger S is the identity, let's think about scattering amplitude using the results above. Let's think about the scattering amplitude for some process where we have, let's imagine we have some particles I. These are going to be momentum eigenstates that we looked at, so there could be any number of them. You don't have to worry too much about this precise details, but we have some initial state I, and these are states of our initial theory, so the in theory. And if we want to calculate the scattering amplitude, the bit that we're interested in is the overlap of our final states, which will in general be different momentum eigenstates in our out theory. So now we can use the definition, or we can put in the definition of the S matrix above. So we can write F out in terms of our I want to do it as, yeah, so I'm using this definition, so I can write it in terms of my in states only, or I can write it in terms of my, in terms of my out states only. So by replacing that, so by using this identity or this relation, this allows me to relate my in state to an out state with this S matrix. It should be I, the out states. Or we can relate it to the in states. Okay, so we can do either. So these are, we can call this thing SFI in general. So this is the matrix element of the S operator. So given some, we've sandwiched it between either out states or in states. So the point is, again, to emphasize, is that we're putting all the information from the scattering process into this operator S. S contains all of the information about the scattering process. There's one particularly simple case we can think about. So we can think about the case where if no interaction occurs, so if no interaction occurs, so we have this in state, it simply propagates from our minus infinity time to our positive infinity time, and nothing happens. So our out state is going to be the same as our in states. Actually, I should use the double label, actually. So my I states are going to be the same for both the in and the out theory. So imagine I've got a particle described by a momentum P1, which is an in state in my free theory. Well, it just propagates freely. It remains as an eigenstate P1, goes to time plus infinity. We identify it as an out state, but it's exactly the same. Nothing has changed. Okay, so what happens in this case? Well, from our definitions above, we see that S must be the identity element. So in this case, S is simply the identity. So in general, we're not really interested in this case. We're not interested in the case where nothing happens. That's pretty boring. Normally, we're interested in the case where some scattering process does happen. So in that case, we expect the identity not to equal, sorry, we expect S not to equal the identity, be something else. In terms of our aim, so we've introduced the Hamiltonian density, or the interaction in terms of the Hamiltonian density. So it's lambda 4 factorial over 5 to the 4. And now we've introduced this operator, this S matrix. And we know that if the interaction is 0, if nothing happens, S is simply the identity. But what we would like to do, general case, is relate this S matrix, this S operator, to this Hamiltonian, this interaction Hamiltonian. Okay, so that's what we would like to do, because we intuitively, we should have a feeling for the fact that the interaction is what's going to determine S. As I said, if the interaction is 0, S is simply the identity. So we want to figure out what happens when it's not 0. Okay, so that's what we're going to start to do in the rest of the lecture. Again, to actually to make this relation, we're going to have to introduce some new machinery, some new techniques. So that's what we're going to do next. Okay, we sort of set up and discussed the basic picture we want to be thinking about in scattering and define this object, the S matrix. So I said we have to introduce some new machinery. So let's go on and introduce it. So the new machinery we need is a new way of thinking about quantum mechanics. Okay, so if you remember, we've already dealt with the Schrödinger picture of quantum mechanics. So in the Schrödinger picture, we had that our states, our Schrödinger states, depend on time, okay, and they evolve according to the Schrödinger equation, while the operators in general do not. So states depend on time, operators do not. We then looked at the Heisenberg picture. In the Heisenberg picture, we swap it. So in the Heisenberg picture, our operators, Heisenberg operators, these do depend on time. Our states do not depend on time. Okay, so the interaction picture, or it's sometimes called the Dirac picture, it's kind of a hybrid of the two. So in the interaction picture, both the states and the operators evolve with time. So let's think about the particular case where we break our Hamiltonian into an H0 piece that we know how to solve. So for instance, the Klein-Gordon piece, plus an interaction piece that's going to involve the terms with interactions. Okay, so what happens in the interaction picture is that our operators, which I'll call OI, I short script I for interaction, this is going to evolve with time according to H0 to only one part of the Hamiltonian, so it's not evolving with the full Hamiltonian. Yeah, it evolves with H0, while our states is also evolve with time, but they're going to evolve with the interaction piece of the Hamiltonian. So what does this mean? Practice. So that's what our operators. So these are evolving with the free piece. So what we have is that the time evolution takes the following form. So if we have our Schrödinger operator, have these e to the I h0 t factors. So this is the same form that we had for the Heisenberg picture, but in the Heisenberg picture, it would have been the full Hamiltonian that enters into the exponential. Here, it's not the full Hamiltonian, it's just the H0 piece. But what you can see with our operators is that in the limit where the interaction piece is 0, we recover the Heisenberg picture. Because and when h int goes to 0, h0 is our full Hamiltonian. Okay, so we would recover the Heisenberg picture. So this is going to be important. We think about our field operators. So using this picture we had above, oops, that's a bit too. So using our picture of kind of interactions. So when we had h not plus h int, so we're doing our Hamiltonian from plus infinity to minus infinity. So our field operators phi at plus and minus infinity, well, at plus and minus infinity, we're assuming that the interaction piece is 0. So our interaction field operators are going to be the same as the Heisenberg field operators. That's true at minus infinity. It's also going to be true at plus infinity. Okay, so it's not true in this interaction regime. The interaction regime, we assume that the interaction Hamiltonian switches on and has effects. But for our terms at plus and minus infinity, find that this does hold. Okay. So this is the general result for how operators will evolve in this interaction picture. Let's think about two particular cases. One is that we can define the interaction Hamiltonian and to be e to the I h0 t h int. H int is the Schrödinger operator. Doesn't have time dependence. So that defines hi. Then, as I said, in general, you can define a field operator as e to the h0 t with the Schrödinger field operator. Okay, so at plus and minus infinity, we see that the interaction is exactly the same as the Hamiltonian picture. And actually, in general, what we find is that the field in the interaction picture evolves in the way that we kind of know how to deal with, okay? Because this is precisely free part of the Hamiltonian, so this is precisely the way the field evolves with time in the theory that we considered previously, in the free theory. So this only involves the free part of the Hamiltonian, so we know how to deal with this. Okay, so those are the operators. Let's think about the states next. So we said that the states are going to evolve interaction Hamiltonian. So let's think about the time evolution of the states. So again, it's useful to start to think about expectation values of operators, switching between these pictures. Let's make this O a bit bigger. So we can start with the Schrödinger picture. Remember, in the Schrödinger picture, it's only the states depend on time, the operator doesn't. Okay, and what we can do is that we can try and write this in terms of the interaction operator. Okay, so in order to make this into an interaction form, we need these e to the I h naught t factors. We can put those in by inserting the identity. Let's insert e to the minus I h naught t, e to the I h naught t, so it's just the identity. So s to e to the minus h naught t, the I h naught t is. Okay. Here in the middle, we have the interaction picture operator. So these bits we should be able to define as the interaction states. In other words, put it off, see that our interaction state is e to the I h naught t times the Schrödinger state. So the reason why this is useful, so we want to figure out the time evolution of the interaction state, and this is useful because we know the time interaction of Schrödinger states. They evolve according to the Schrödinger equation. So let's figure out then exactly what the time evolution of these interaction states are. So we do this by differentiating both sides. We're doing I times the derivative, so let me remember this factor of I. So we differentiate the exponential. And then we differentiate the state. Okay. So from the first term, we get, well, we get an I times an I factor, so we get a minus 1. Minus h naught. Then this bit, the e to the I h naught t psi s piece, this is simply the interaction state. Call it psi t. That's the first term, and from the second term we get e to the I h naught t. Then we shouldn't forget about this I factor, so then we have I times d dt. So this is just the this would be 1/2 of the Schrödinger equation. So we know that I times d dt psi is the Hamiltonian times state, acting on the state. So this is going to be the Hamiltonian, and it's the Hamiltonian of the full theory, so it's h naught plus h int acting on our state. Okay, so what do we have here? Well, we have minus h naught interaction state plus, well, we've plus e to the I h naught So we can pull the h naught through because h naught commutes with itself. So we get plus h naught, and then once we pull h naught through to the other side, we're left with e to the I h naught times psi Schrodinger, which again, just to remind you, is the interaction term. So we'll get plus the interaction piece. And then we have one final thing that we have to deal with. The final piece that we have is e to the I h naught t h int I s t. Let me fix it. I s t. Okay, so obviously these two will just cancel. Okay, simple. And this doesn't look super helpful at the minute. It would be more helpful if we were able to write psi s, or rather if we could write it in terms of psi I instead of psi s, because then what we really want is a differential equation only involving the interaction pieces. But okay, that's reasonably straightforward to do. Okay, we can invert this equation, or we can multiply both sides by the inverse operator, e to the minus I h naught t. So that will give us a factor 1 here. Leave us psi st. Do that, we'll get e to the I h naught t int. Or the other way to think about it is you can just insert the identity. We write as this. Okay, and the reason we want to do this, so as we said, this is psi I, and then the other piece we will identify as hi, so what we defined above. So this is e to the minus I, sorry, e to the plus I h naught t times the Schrodinger interaction Hamiltonian times e to the minus I h naught t. This is exactly the term that we have here. This is going to be our h t, please. Okay, so what we found then is the time evolution. So it's the equation satisfied by it's up by this interacting state. So I dt is simply h t it. So that's a nice looking equation. Looks a little bit like the Schrodinger equation, but not only involves our interaction states. Okay, so we're really running out of time, so let me just summarize what we've shown so far. There's quite a bit in this lecture. So we introduced this phi to the 4 theory, or well, we talked about interactions generally, but we then focused on this phi to the 4 theory that we're going to look at. We introduced some basics of scattering theory, so thinking about how you can set up scattering problems. And we introduced this important object, the S matrix. And then in order to make progress, we've had to sort of take a little bit of a stop. So we introduced this interaction picture, and we thought about the time evolution in the interaction picture, and derived this formula due to Dyson's formula. Next, what we want to go on and do is relate our S matrix to this Dyson's formula in some way using this interaction picture. So that's what we'll pick up in the next lecture.